So, good morning to all. So, I think today I've been asked to talk about numerical weather prediction methods. So, I understand most of you have complete background. If there's someone who doesn't have a background in physics, so on fluid mechanics, then I will just have to spend a little bit time. But anyhow, just for completeness, let us start. So, both the atmosphere and the ocean are fluids, right? And we know fluids are, the examples of fluids are gases and liquids. Now these two look very different from one another, but they have something very common underlying property or characteristic. That underlying characteristic is what we use to define fluids itself. So we define fluids as a substance which yields to shear stress. So fluid is something which cannot resist shear stress, however small the shear stress be. So that is how we define fluids. And all of you know about the Newton's law of viscosity that relates the shear stress to the rate of strain. And if this relationship is linear, we call such fluids as Newtonian fluids. And fortunately, both the atmosphere and the ocean, the air and water, both of them are Newtonian fluids. And you would have, so the most important thing that we first deal with fluids is, the fluid is a continuum. Now this is some hypothesis all of you must have heard called the continuum hypothesis. Essentially it makes our life a lot easier. The basic understanding is fluid is something which is continuum. It's going to be a continuous thing. There's just no gaps between fluids, and that helps in various ways. So the requirement is for this continuum hypothesis to hold, we need to follow the certain criteria, or the condition has to be satisfied. That condition is the characteristic length scale of any fluid flow has to be very much larger than the mean free path. Now we know what is mean free path, which is average distance between two molecules, between a molecule between successive collisions. And in the atmosphere, the mean free path close to the surface has a value of 10 power minus 7 meters. Now we cannot imagine any fluid flow in the atmosphere which has a characteristic length scale less than 10 power minus 7 meters. So for all practical purposes, the continuum hypothesis must hold. Now only if you go to heights above 100 kilometers, the mean free path can assume values of the order of a meter, and possibly the continuum hypothesis may fail at such great heights. Then of course we'll have to invoke the molecular viewpoint and deal with fluids from the molecular perspective. Now, as far as weather prediction is concerned, we are not going to deal with heights above 100 kilometers. So we are practically comfortable that we are under the realm of continuum hypothesis. Now, once we agree that continuum hypothesis is applicable to the atmosphere and the ocean, then the following question arises. How do we describe fluid motion? So the most convenient way to describe it is to imagine or envisage what's called a fluid element. Now the fluid element has there's no proper definition for it, but then it's of so much use to us that we just use it. So one can simply define a fluid element as to be made up of billions and billions of molecules. So large number of molecules and of such a size that we can actually ascribe macroscopic properties to fluid. Otherwise you can't define temperature for a molecule, but you can define temperature for a fluid element. So that's the whole idea. And the concept of fluid element is very important for us because all the physical conservation laws, the basic conservation laws of mass, momentum, energy, all those things can be very easily applied using this concept of fluid element. Like for example, if I have a fluid, okay, before I come to that, I'll have to talk about very briefly about, once you have fluids that are made up of fluid elements, and with time the fluid elements are going to move. Now how are you going to describe the motion of this fluid element? Now fundamentally there are two ways of describing fluid motion. One is what's called the Lagrangian description, and it's called the Eulerian description. In the Lagrangian description, what is done is you identify a fluid element, mark it, track it in all its trajectory, in all its history. So essentially you follow a identified fluid element during its course of its motion and see how its properties, fluid properties are going to change with time. That in essence is the Lagrangian description. You may have to do it for maybe 1 lakh or 10 lakh or 1 million fluid elements in order to get a full perspective of the fluid motion and how the fluid properties are going to evolve in time. The alternate description of fluid motion is what is attributed to Euler, which says that we are not going to identify a fluid element, mark it and track it. So instead we are going to fix the reference frame And then obviously every fluid element in my fluid domain is preferentially located with respect to the center of origin of this reference frame. And if you assume you have temperatures of all these fluid elements, so the temperature essentially becomes at a fixed time, then it becomes a scalar field. Similarly, you can talk of density as a scalar field, pressure as a scalar field. And if you ascribe velocity to the different fluid elements, then the velocity becomes a vector field. So then it turns out that, so in the Eulerian description, we are not looking at a fluid element, we are looking at a point in space, and obviously with time different fluid elements are going to occupy that point in different times. So obviously the fluid properties are going to change, and we have a basic relationship how this rate of change of a property following the fluid motion in a Lagrange description can be related to the Eulerian description. So I don't have to go into all these things, I'll just write this down. If temperature is T, then this is called the total or the substantive derivative. So this means that the rate of change of temperature following the motion of fluid element, and this we know is called the local derivative plus, okay, so this is the total or substantive derivative, this is the local derivative, this is called the advective term, advective derivative. So basically the right hand side is the Eulerian description, the left hand side is Lagrangian description, and so we know if we deal with one description, it's possible for us to write the governing equations in the other description and vice versa. So this is the basic thing that relates, and of course you can apply it to vector field also like velocity. Okay, now with this, let's look at how do we invoke the conservation laws of physics. So if I have a fluid element, let's take the conservation laws of mass. So let's assume that I have a fluid element of a mass delta m. So this statement tells you that the mass of the fluid element following the motion is not going to change. That's a statement of conservation laws of mass. So the conservation laws, as you can see, are very easily explainable, or one can easily explain it or invoke it using the Lagrangian description. So the same way one can also talk about the conservation of momentum. So you have a fluid element. Now you can have different types of forces that act on a fluid element. Broadly we characterize the forces as surface forces and body forces, and you find out what's the net force that is applied on the fluid element and use Newton's second law of motion, relate the net force per unit mass to the rate of change of momentum. So that's my conservation of momentum equation. So it's very convenient to invoke and use this concept of fluid element to apply your conservation laws of physics. Coming to conservation law of energy, so it's nothing but the first law of thermodynamics. Again the same thing, you have a fluid element, you know at the rate at which the heat is added to this fluid element, this partly goes to increase the rate at which the internal energy can increase, and the remaining would be the rate at which the work is done. So essentially all your basic conservation laws can be very easily applied to this fluid element, and that essentially is what we are going to do. The only difference is, now we have the winds in the atmosphere, we have the currents in the ocean, and these are basically motions that we would want to describe. So ultimately we are interested in the motions of the atmosphere in the ocean, and then we would like to know how these winds and the ocean currents change with time. So evolution of these in time, that's essentially my fundamental aspiration or objective. Now obviously, what is the most convenient way to describe the motion in the atmosphere and the motion in the ocean? The most convenient way to describe it would be for an observer who is standing on the earth. Now for an observer standing on an earth, he is going to observe it from a reference frame which is fixed to the earth. Now any reference frame which is fixed to the earth turns out to be a rotating frame. And we all know rotating frame is not an inertial frame. So once it's not an inertial frame, Newton's laws of motion cannot be applied, right? So we have to find a workaround solution for this. And so what we do is, we look at a rotating frame and then find out what are those acceleration terms that are responsible for the departure of the inertial behavior. So we have two acceleration terms for our planet Earth, because the angular velocity turns out to be constant. So we have what's called the centripetal acceleration, the Coriolis acceleration, and these are dealt with as fictitious or pseudo forces as Coriolis force and centrifugal force. Now, sorry, the centrifugal force in general is combined with the Newtonian gravitation force to define the effective gravity. So in a sense, we can handle this conservation of momentum as in a rotating frame by the strategy, by the procedure that I just outlined. Okay, so let me start my. Okay, overview is introduction to NWP, a historical perspective, method of finite difference, something about linear stability, aliasing nonlinear computation stability, semi-Lagrange semi-implicit method, Galerkin spectral method, and then I will end up with need for data assimilation. Okay, so I have already given some. So basically, if you look at Edmund Halley was one of the pioneers scientists who made the important contribution about the dynamics of the tropical winds, and he ascribed this, attributed this to the solar heating. And of course, Hadley in 1735 included the effects of the Earth's rotation to modify the Halley's theory, and then Ferrel in 1858 applied the Coriolis force to the atmosphere. Of course, 1755 Leonard Hall Euler gave the governing equations for the inviscid fluid flow. Inviscid fluid flow would mean flows that are inviscid, which is non-viscous and incompressible. Then Navier in 1822 and Stokes in 1845 extended the equations, governing equations of Euler for the potential flow to include viscous effects. And we have this well-known Navier-Stokes equation that came up in 1845. Then Reynolds made the seminal contribution that deals with transition to turbulent flow sometime the beginning of 20th century. And of course, this is where we start. Biaknis was one of the most, what I should say, famous atmospheric scientists. In the beginning of 20th century, you can say he's the father of numerical weather prediction. So he presented his rational version of forecasting based on the laws of mechanics and physics. So before I go into it, so now all of you are familiar with a simple pendulum having small displacement, right? So we write this as theta is the displacement, t is the time, omega is your angular frequency. So obviously for small displacement becomes a linear second order ordinary differential equation, and then immediately I can write down the solution. Now in order to find the solution, now I have A and B are the independent constants for integration. So in order to find out A and B, I need to prescribe the initial displacement as well as the initial velocity. So once these are known, I can substitute here and find out the values of A and B and get the solution. So this whole thing, the differential equation along with the initial condition is what's called a mathematical initial value problem. Now Biaknis in 1904 proposed that the numerical weather prediction is nothing but a mathematical initial value problem. So essentially, there are two requirements for a mathematical initial value problem. One is the initial conditions. So that would mean, as we apply it to the atmosphere, that would mean the initial state of the atmosphere. And second would be the equations for simple pendulum here that would correspond to the governing equations that evolve, that are responsible for the evolution of the atmosphere as a system. So once you have these two, so in principle, one can apply the numerical methods and then find out what's going to be the state of the atmosphere at a later time. So this was the idea proposed by Biaknis in 1904. So that's what any system that evolves changes in time is called a dynamical system. We can assume the atmosphere to be a dynamical system. So the requirement is we need to have a set of rules and laws that govern the time evolution of the dynamical system and complete information of the initial present state of the system. So 1904 he proposed that weather forecasting or NWP is a mathematical initial value problem. And 1922 Richardson, who was a British meteorologist, really took up the challenge of implementing this idea of Biaknis. Now you recall that 1922, there was absolutely no information. We all know that 70% of surface area is covered by ocean. There's practically no information about the ocean. Satellites and all came much later. 1960 was the first meteorological satellite, April 1st. So there were no conventional observations and very little upper air observations available. So, but still, he was convinced of this idea. Richardson was convinced of this idea that it's possible to employ numerical methods. And if you see the efforts that he undertook in 1922, practically there's no difference between the efforts that he took that time, applying numerical methods, to the present modern numerical weather prediction. So essentially it's the same. So, however, what happened was, that was during the end of the First World War, and then he took a lot of time. In fact, he is supposed to have taken 6 months to give a forecast of 3-hour pressure change at London, and then 6-hour pressure change turned out to be 145 hectopascal. 1 hectopascal is 100 pascal. So obviously it's clearly something terribly wrong. You just cannot have a pressure change in 6 hours of 145 hectopascal. So this was a big disappointment at that time. It was so disappointing to all the atmospheric scientists that nobody ventured into numerical weather prediction until 1950. So 30 years nobody touched this. They thought this is something beyond everyone. Okay, so it's a very nice, interesting experience of. Okay, so this is something which is known to all of you. Later it was discovered that the atmospheric equation, initially when Richardson got this value, people all attributed it to the poor initial data because practically no data was available. Everyone was convinced that without the proper prescription of the initial state of the atmosphere, obviously you're going to have very, very wrong results as far as the forecasting of the future state of the atmosphere is concerned. So everybody attributed the sort of disappointing results of Richardson to the fact that very little data was available for him to actually use it because the upper air data was not available. So subsequently, late 1940s and early 1950s, Charney in his research discovered that atmospheric motion is complete form, admits solution not just of the slowly moving Rossby waves but also the fast moving sound and gravity waves. So this high speed waves amplify spuriously with time and masks the solution. So Charney proposed that if only one were to do numerical forecast, one would have to control this or use some filtered set of equations that do not take into account this high speed waves and deal only with the meteorologically significant Rossby waves. And then 1950, the first successful numerical forecast was carried out under the leadership of von Neumann, Jules Charney and Fjordford. And 1945, ENIAC, the first computer was designed. And the first task with this ENIAC was assigned to was the weather forecasting. And so in 1950, they successfully brought out the first numerical weather forecast. So after 1950, there's been rapid progress in all aspects of numerical weather prediction. This is largely to the increased quantity and quality of the meteorological data. That includes satellite data that became available from 1960 onwards. Then advancements in the telecommunication system, tremendous progress in computer technology, and development of much better and sophisticated numerical models. So this is, I thought, be not out of place to put some 4 slides. Basically, this is Richardson's efforts at his own numerical weather prediction in his own words. So basically, he says if the time step were 3 hours, now all of us know one cannot have a time step of 3 hours because it was, the CFL condition was not known. It came much later in 1940s and Richardson was not aware. So of all this, the fact that your choice of the time step would critically depend on your grid size as well as the wave speed of the fastest moving wave. So basically what Richardson said was it's time step for 3 hours and 32 individuals are assigned to compute 2 points to keep pace with the weather. So he assumed a grid size of 200 kilometers square, and then he says there are 3,200 columns on the complete map. Now if you actually take the 4 pi r squared is much larger than that. So obviously he thought oceans are something which is not important and possibly you won't have data, so there's no point in forecasting So basically the 3,200 columns that he thought or envisaged were columns only over the land. And then in his views, tropics, the weather is often foreknown, things don't change at all. So 1,200 out of the 3,200 columns can be taken away from the tropics, because 30 north to 30 south accounts for something like 50% of the surface area. So we can remove like 1,200 columns, so only 2,000 active columns you need to find. And for each of the active columns you need 32 people. So you need 64,000 people to compute the weather. Okay, that was his first. So he says 64,000 computers would be needed to raise the weather for the whole globe. This is a staggering figure. I mean, this was written in 1922. But in any case, the organization, so what he imagined was you need to have a central forecast factory for the whole globe, and where the weather is steady with individual computers specializing on the separate equations. Now he used this word computer, which was actually not known. So all he meant was a human calculator. So imagine a large hall like a theater, except that the circles and galleries go round through the space usually occupied by the stage. So the walls of the chamber are painted to form the map of the globe. So different parts of the theater walls are different continents. So ceiling is the North Pole, England is in the gallery, tropics in the upper circle, Australia in the dress circle, and Antarctic in the pit. So you have computers are at work upon the weather of the part of the map where each sits, but each computer attends to only one equation or part of an equation. So you have, I'll show in the later slide that we have 7 governing equations that represent the basic equations for the evolution of the atmosphere. So he says there are people working for one particular part of the globe. They will solve some equation, part of an equation, or one full equation. The work of each region is coordinated by an official of higher rank. Numerous little light signals display the instantaneous value so that the neighboring computers can read them. So obviously there is a need for what is the state of the atmosphere or winds, temperature and humidity at one place, the other person should be knowing that. Each number is thus displaced in 3 adjacent zones to maintain communication to the north and south of the map. From the floor of the pit, a tall pillar rises to half the height of the hall. It carries a large pulpit on its top. In this sits a man who is in charge of the whole theater. So he is the chief forecaster. So one of his duties is to maintain a uniform speed of progress in all parts of the world. So he should ensure that whatever this forecasting or updating the state of the atmosphere in future has to be done in the same time by all the so-called computers over all the regions. So no computer should be lagging, no region should be lagging behind some other region. So the person who is in charge has to ensure that this forecast or this thing updating of the state of the atmosphere happens everywhere uniformly at the same time. So he has to maintain uniform speed and progress. He's like a conductor of an orchestra in which the instruments are slide rules and calculating machines. But instead of waving a baton, which a conductor does, he turns a beam of rosy light upon any region that is running ahead. So somebody is doing very quickly, he'll show a rosy light, tell them to slow down, and if somebody is lagging behind, he will show a blue light. 4 senior clerks in the central pulpit are collecting the future weather as fast as is being computed and dispatching to the carrier to a quiet room from which it will be coded and telephoned to the radio transmitting station, so that the public at large will get to know what's the state of the weather at a later time. So messengers carry piles of used computing forms down to a storehouse in the cellar. In a neighboring building, there is a research department. Now he imagined that now the way of forecasting is a problem which is going to be never ending. So there has to be a lot of research that should happen, and research cannot happen in the operational sort of scenario that he envisages. So that has to be undertaken by specialists, by different sort of people in an adjacent building. So they will invent improvements of how to improve the forecasting scenario. So in another building are the usual financial correspondence and administrative offices. Outside are playing fields, houses, mountains and lakes, for it was thought that those who compute the weather should breathe in it freely. So this is a remarkable vision of Richardson, in which he meant computers mean only one thing, a human calculator. So from 1920, from the Richardson stage to the beginning of the successful numerical forecast 1950, there was progress in various various, what I should say, fronts. One is the CFL condition, the Coran-Frederick-Lewis condition, which essentially sets up the time step to be chosen, was proposed in 1940. Then better people started realizing about the nonlinear computational instability, and then one started designing schemes that actually solve this PDE accurately and efficiently with numerical methods. Of course, it had to wait for 1960s before Professor Akio Arakawa of UCLA could propose a roundabout, a workaround solution for this nonlinear computational instability. Of course, after 1920s, the radio sondes became very common, and then you had this World Meteorological Organization having the overseeing capability of the data being collected and being transmitted and used by all over the world. Then of course, invention of the electronic computers enhanced the efficiency of the scientific calculation. So basically, as I've told you, the basic equations are 7. So the first 3 are the equations those are the zonal component momentum equation, meridional component momentum equation, and the vertical component momentum equation. Then the 4th equation is the thermodynamic energy equation. This is the conservation of energy. The first 3 are statements of conservation of momentum. Then the 5th equation is the conservation of mass. The 6th equation is the conservation of moisture. And the 7th equation is basically the equation of state for ideal gas. So we have 7 dependent variables: U, V, W, T, rho, Q, V. Alpha is 1 over rho, so it's not a dependent variable. So we have 3 velocity components: temperature, density, pressure, and moisture. So we have 7 equations, so we have a closed form. But if you see the last terms in the first 3 equations, Frx, Fry, Frz, those are the frictional force per unit mass terms in the x direction, in the y direction, and the z direction. And then dH by dt, the right hand side last term in the 4th equation, is nothing but the diabatic heating term. So these are the terms that basically deal with physics that has to be dealt with separately. Okay, now we come to how do we solve this equation. So the first and foremost method that was sought to be invoked to solve these equations are known as finite difference equations. So let us take a simple equation like the one-dimensional linear inflection equation, dou u by dou t plus c dou u by dou x equal to 0. So obviously we know that we have this as an analytical solution, and any function f of x minus et is a general solution for this equation. However, if we have to solve this numerically, what is done is the continuous domain is discretized into a discrete domain. So the continuous one-dimensional from x equal to 0 to x equal to L is now divided into a finite number of grid points with choosing a particular grid size delta x. So the discrete values of x are xj is equal to j into delta x. So j is an integer that can run from 0, 1, 2, 3 and so on. So similarly that we have to discretize time also. So the continuous time t is discretized, Tn is equal to n into delta t, where the delta t is a time step that actually discretizes. So n again can vary from 0, 1, 2, 3 and so on. So delta x is a grid space and delta t is a time step of integration. So one can write down, so what we do is the derivative dou u by dou t is replaced with by using Taylor series expansion and retaining only the linear term, the expansion in time, and then you can write down the finite difference form, which is the first term, what you can see here. So j is the space index, n is the time index, uj n plus 1 minus uj n by delta t, it tells us that is the forward marching in time, delta t is a time step. And see, if you assume to be constant, I replace this dou u by dou x again by forward marching in time. So this is actually backward marching. This is at time n, j, and this is j minus 1. If actually c is positive, then this is nothing but your upwind scheme. So what I have done is I have replaced the continuous partial differential equation with a discrete finite difference equation. Now there are 2 questions arise. Firstly, so I have used Taylor series expansion to get this discrete form from the PDE. Now can I recover the PDE? That's the first thing which we have to see. So again, it's like I have a function, I have differentiated it, so I integrate it, I should get back the original function. So what we have to do is we use the same Taylor series expansion and replace the differences in terms of derivatives, and in the limit delta x tending to 0, delta t tending to 0, we should be able to recover the original PDE. If a finite difference scheme has that property of recovering original PDE in the limit when delta x tends to 0, delta t tends to 0, then we say the finite difference equation is a consistent scheme. So the first requirement is the requirement of the scheme being consistent. So now if this is not the case, what will happen? Essentially you will solve by numerical methods the discrete finite difference equation, but in the limit delta x tending to 0, delta t tending to 0, if the scheme is not consistent, the numerical solution will be giving the solution of some other partial differential equation, not the linear advection equation. So this is the first requirement for the FDE finite difference scheme to be a consistent. Next is of course obviously you want the finite difference solution to converge to the original solution of the PDE. Here we have indicated small u is the solution of the PDE and capital U is the solution of the finite difference equation. So again we would want in the limits delta x tending 0, delta t tending 0, the solution of the finite difference discrete form should converge to the solution. So for this to, there is a theorem called lax equivalence theorem, which was proposed sometime in the year 1940. So which says that for any partial differential equation which is well posed, any finite difference form, any finite difference scheme can provide for a convergent solution to the original PDE, provided there are two conditions that have to be met. One is the scheme has to be consistent, and the second requirement is the scheme has to be stable. Now in very simple terms, what do you mean by stability of a finite difference scheme? Suppose at some particular time, at some time with an index n, let's say epsilon is the error of the finite difference solution. Suppose epsilon n plus 1 is the error of the finite difference solution at the time step n plus 1 index, and if I divide that by the error at the previous time, this should be less than equal to some tolerance. Okay. So sorry, less than equal to 1. So what it essentially means is the error should be bounded. Now if this were greater than 1, so every time step, every time marching, the error would increase, and after some time the error will grow without bounds. So in order for the finite difference scheme to be stable, we need to have this condition. So this is called the amplification factor. The amplification factor has to be always less than 1. Okay, so this is exactly what was for the one-dimensional advection equation. Coran, Frederick and Levy proposed in 1940 that for a one-dimensional case, so this is the requirement. The delta t time step should be chosen in such a way that C delta t by delta x, which is known as the Coran number, has to be less than equal to 1. So unfortunately Richardson was not aware of all these things, so he took a much larger time step and then obviously got a solution which was very weird. So okay, now if you look at these governing equations, now so you can see here, so clearly this term, this advective term is a nonlinear term, right? So this nonlinear advective terms appears in the first 3 terms, the first equation, second equation, third equation, okay. So obviously you have the nonlinear term, and because of this appearance of the nonlinear terms, in 1948 when Phillips tried to integrate the baroclinic model, atmospheric model, he faced a real situation. Now unlike the linear stability criteria as proposed by Coran, Frederick and Levy, which required this, now in this case what happens is the instability doesn't grow rapidly. So you have a general growth of the error, and at some particular time it will blow off. But when you deal with nonlinear set of equations, the instability is sudden and without any notice, okay. So Phillips called this nonlinear computational instability, and then this was a serious issue. And he clearly identified that this instability is happening because of the appearance of the nonlinear terms. And then he actually found out why it is happening, but he was not able to find a workaround solution for that. So we will clearly see now what is this nonlinear computational instability, which is also known as aliasing. So many of you would have known the term aliasing. So let's say that, okay, suppose I have a one-dimensional grid of grid size delta x. Okay, now this is delta x. Now the question is, what is going to be the smallest wave, or the wave with the smallest wavelength that can be represented in this? Because at the end of the day, all those equations are hyperbolic, it's quasi-linear first order equations, and they are all have to be essentially hyperbolic. Now we know hyperbolic solutions are wave solutions. So now the question is, I cannot have a wave like this. Clearly not admissible. So if this is admissible, then this also should be admissible, right? So the smallest wave that is admissible and is resolvable is the wave like this. So this requires the wavelength to be 2 delta x. So the smallest wave that can be resolvable with a grid delta x is 2 delta x. And so this is the smallest wave, I can say minimum wavelength. And this would correspond to the maximum wave number 2 pi by minimum wavelength, which will be pi by delta x. Okay. So here you see in this case, so the distance between two dots is delta x. So clearly, if you look at the continuous line, so that's a wave. Now what is the wavelength of the wave? It is larger than delta x but smaller than 2 delta x. It is actually 4 by 3 delta x. Clearly 4 by 3 delta x is less than 2 delta x. So this is not a resolvable wave at all. Okay. What happens essentially in this aliasing and nonlinear computation instability is, if you see the dotted line, now at the grid point, which is those dots, there is no difference between the continuous line and the dotted line. Can you make out? So you see here, there is no difference. At the next grid point, there is no difference. At the next grid point, there is no difference. At the next grid point, there is no difference. So the continuous wave, which is not a resolvable wave, actually appears or manifests or aliases as a resolvable wave. The resolvable wave is the dotted line, and if you look, what is the wavelength of the dotted line? The half the wavelength is 2 delta x, so that means the wavelength is 4 delta x. So this is your continuous, and this is your dotted. So what is really happening is, a wave that is not resolvable is actually represented as a resolvable wave. So obviously it's a clear serious error. So now why is this happening? So this happens only if you have nonlinear terms in your differential equation. So let's take two modes A and B. They are having the, okay, this should be wave number k and l having amplitude say naught. So you represent A as some amplitude into the harmonic form e power I k j delta x. J delta x is nothing but x. J delta x nothing but x. So here k is the wave number, l is the wave number for B. Now if you have a product term, nonlinear term, which is the multiplication of A and B, so this is the product. The exponents k and l add together and you get this. Now what happens if you have a nonlinear term? This k can have, suppose the grid here is discretized into a grid size of delta x, here also delta x. So the highest wave number can have a value of pi by delta x. So k can have a value pi by delta x, l can have a value pi by delta x. So k plus l can have a value 2 pi by delta x. 2 pi by delta x is larger than k by delta x. So clearly that's not acceptable. Okay, so that's not acceptable. So let's look at this to understand what really is happening in this nonlinear computation instability. So we will consider, now this is K, this is K max pi by delta x. So let's take a K which is larger than K max. So the corresponding wavelength of this will be less than 2 delta x. So I take a value of K between K max and 2 K max. So here K max is equal to pi by delta x. So 2 K max is equal to, so let's calculate, so we will consider a K which is between K max and 2 K max. Clearly this is a wave which cannot be resolved in the grid having a grid size delta x. What's really happening? So if you calculate sine of Kj delta x, okay, just show it. Is there a pointer something? A pointer is there, okay. So sine k delta x is equal to sine of, I add and subtract 2k max here, okay, and then 2k max into j into delta x. 2k max into delta x is nothing but your part, you can see here. 2k max delta x is nothing but is equal to 2 pi. So I just replace that with 2 pi. Sorry. So I am adding and subtracting 2k max, okay. J delta x is common. Now 2k max into j delta x is nothing but 2 pi into j, which I am writing here. The other terms I am combining here. Now this is sine a minus b, which is sine a cos b minus cos a sine b. Sine of 2 pi j is going to be 0. Cos of 2 pi j is going to be 1. Okay. So this, now you get this, and this this minus of 2k max minus k I can represent as k star. Similarly, if I write an expression for cos, I'm going to have this. Again, k star and k are going to be related like this. So if you, let's take this example, whatever we have worked out. So for the example that we got 4 by 3 delta x, okay, and okay, so what is the corresponding k for this? 2 pi by 4 by 3 into delta x, 3 by 2 pi by delta x. So clearly 3 by 2 pi delta x is larger than pi delta x. So let's take this value. This is pi by delta x, this is 3 by 2 pi by delta x. This would be 2 pi by delta x. So how this non-resolvable wave number is going to appear? So if you calculate, so k star is your 3 by 2 pi by delta x, that is equal to your 2 k max minus k. Now what is k max? K max is pi by delta x minus k. So k is going to be 3 by 2 pi delta x minus 2 pi by delta x. Okay, so you have this minus sign there. Okay. So k is equal to, so this would be plus, and so k is going to be this. So you have 3 by 2 plus 2 by, so this will be 4 by 2, 7 by 2. I think there's a mistake somewhere. K star is 2 pi by, this is wrong. So 3 by 2 delta x is clearly so that is equal to minus 2k max minus k. So this would be k pi by delta x. Okay. So it's fine. It is 7 by 2 pi by. So if you look back, okay, if you don't, then it becomes minus 4. So this is going to be minus pi by 2 delta x. The corresponding lambda is going to be 2 pi divided by k. That is going to be pi by 2 delta x. So this is what was happening. So this continuous line which had a k wave number of 4 by this wave number 3 by 2 pi delta x, which is larger than pi delta x, the maximum wave number allowed, is actually representing itself as a wavelength, as a wave whose wavelength is 4 delta x. Okay. So, so this is a workaround solution for this nonlinear computational instability was provided by Arakawa, as I told, in the year 1960. We will not really go into those details. So now the question is, so before Arakawa gave his workaround solution for this nonlinear computational instability, people started realizing, okay, the nonlinear computational instability is happening because you are dealing with nonlinear equations, right? Now, where did this nonlinear equation, where did they come from in my governing equations? They came from, they were manifesting themselves as nonlinear advective terms. And these nonlinear advective terms were arising because of, I was describing the fluid motion from an Eulerian viewpoint. Now, if I don't write down the equations from Eulerian viewpoint, rather I write them from a Lagrangian viewpoint, then there won't be nonlinear terms. If I don't have nonlinear terms, I will not have to deal with nonlinear computational instability. I will not have to look for workaround solutions how to overcome this aliasing. So scientists started looking at Lagrangian description of fluid motion and the corresponding equations in a more serious way because of this nonlinear computational instability. So and then a new set of methods came into being which are known as semi-Lagrangian methods. Okay, so people started looking at the Lagrangian equations. So now let's take a simple example. Semi-Lagrangian essentially means it's not completely Lagrangian, it's partly Lagrangian and partly Eulerian. So we know that, like, for example, if you have an incompressible fluid flow, we all know that the rate of change of density following the motion of the fluid element is going to be 0, right? And then you have the continuity equation in the so-called simplest form, the non-divergent form. So suppose I have a equation. This is conservation equation. Let's say it says that the rate of change of F following the motion of a fluid element or an air parcel is 0. So F is a conserved quantity following the fluid motion. So this is your total or your substantive derivative. And if you have to write it in the Eulerian description, then you write this as, in one-dimensional case, you will possibly write it like this. And then U is unknown, F is an unknown, so you have a nonlinear advective term. So I don't want to deal with this, I want to deal with this. Okay, now how do I do this? So let's take a simple one-dimensional case, and because semi-Lagrangian, we again have a discrete grid. So this is in x direction and this is delta x. The question I ask is, suppose I have a fluid element here. Okay, now let's say this is x and this is time. So let's take, So this is Tn, this is Tn minus delta T, this is Tn minus 2 delta T. Okay. Now these are different values of x divided by delta x, this is divided by delta T. Now let's take a point here. So I have a fluid element or an air parcel or a water parcel, whatever, at this location at this time. Now I ask the following question: from where did this, what was the location of this fluid element 2 delta T times before? And if I know what is the location of the departure point of this fluid element 2 delta T times before, then I can discretize this equation as f, the present position, which is like xd at time Tn minus f xd minus 2 alpha I can discretize this as this. So the present location is xd at the present time Tn. Okay. So if I discretize this is the functional value at this location minus the functional value at the location of the departure point. I don't know what this is because I don't know alpha. And then this is minus 2 delta T. Sorry. 2 delta T times before. Now I have used central difference here. Pi 2 delta T is going to be equal to 0. Okay. So obviously this means this is equal to 0. So if I want to know what is the value of f at the present time at this present location, all I have to do is find the value of f at the location of the departure point of the same fluid element 2 delta T times away. So if this is my location of the departure point of this fluid element 2 delta T times away, then I know what's going to be the value of f here because it is 2 time steps before, right? So once I know what is the value of f here, I reassign the value of f. That's all. Got it? I see only blank faces. This makes sense or no? So here we are dealing with Lagrangian. So basically I have a fluid element, let's say, okay, let me write it down. Okay, this is the trajectory of the fluid element from the present time to 2 delta T times before. Now this is the trajectory, but I don't know the trajectory. Since I don't know the trajectory, I don't know the displacement. Right? Since I don't know the displacement, I don't know where is the center of the displacement. Since I don't know where is the center of displacement, I don't know what's the value of the fluid velocity at the center of displacement. Okay. So let's say that this is my okay, now what I'll do is I'll approximate this by a straight line. So this straight line will be falling at this grid point. So let's say C prime. So ABC, which is the exact trajectory, is now replaced by approximated by a straight line, which runs through. Now this also need not go through a grid point. The straight line also need not essentially have to go through a grid. So what it means is, if I know what is the location of the departure point 2 delta T times before, what is the value of f at the present time is what I want to know, is equal to the value of the f at the location of the departure point 2 delta T times before. So that is essentially what this. So I have to find out what is the location of the departure point. This I have to find out. Now how do I find that? Now if you look, this is x, this is time. So the slope of this curve is nothing but delta T by delta x. So the slope here is 2 delta T. Let's take, so that this distance is equal to 2 alpha. The displacement from the present time to 2 delta T times before is 2 alpha. So basically 2 delta T by 2 alpha is equal to, the slope is delta T by delta x is reciprocal of the velocity. Reciprocal of the velocity, let's say I'm representing the x component of velocity by capital U. Now what we do is we represent this velocity at the center of this from t to t minus 2 delta t. So obviously it should be at t minus delta t. What about the value of x? It should be exactly midway between my beginning point and this. So obviously the beginning point is xd minus alpha. Does it make sense? And so 2 and 2 will cancel. So alpha is nothing but delta t into u. Now you see here, to find out alpha, it depends on capital U and depends on capital U at the midpoint of the trajectory, which again depends on alpha. So alpha is implicitly dependent on itself. So what it essentially means is, if I have a trajectory, to find out the location of the departure point, I replace the actual trajectory by a straight line curve, write down the relation between the slope related to the reciprocal of the velocity and reciprocal of the velocity at the center point, at the midpoint between t and t minus 2 delta t, that is t n minus delta t, at the midpoint of the x location. Here it is xd, here it is xd minus 2 alpha, so the midpoint would be xd minus alpha. So I get this relationship. So I have to solve this iteratively and find out alpha. So that is what is written. So the superscript r is actually iteration number. So instead of capital U, I have written A. Okay, that's the only difference. So if you want to see, you can see this. Previously, I have written. So you can see dx by dt is equal to A. So I am representing as it's the velocity. So I solve this iteratively, find out the alpha. Once I find out alpha, I find out 2 alpha. 2 alpha, the present location xt minus 2 alpha is going to give me the location of the departure point. And this location of the departure point need not be a grid point, right? And if this is not a grid point, so I know the value of f here, I know the value of capital F here, 2 delta t times before, and I can interpolate and find out the value of f at that location of the departure point. And that would be my right hand side, I just reassign it to the left. So like that, if I now take this point, present time this is a location, what is the location of the departure point of the fluid element which is presently here 2 delta t times before. So I solve those equations, iterative equation, find out alpha, find out 2 alpha, and then so find out what's the location of the departure point, interpolate and get the value of capital F at that point, and then reassign. So this is what we have to do in a semi-Lagrangian situation. So this is what it is. Okay. So there is also another method called semi-implicit method. Okay. So these are the well-known shallow water equations, two-dimensional full nonlinear shallow water equation. Now the terms that are underlined are basically the terms that are responsible for the gravity wave. You have the pressure gradient force terms and then the divergence term in the shallow water equation. Now in the semi-implicit scheme method, we have to deal with this underlined terms in a very special way. That means we have to deal with them implicitly. All the other terms you can deal with them explicitly. So that is the essence of the semi-implicit method. Okay, there is a typo here. So you can see that all those equations, un plus 1 minus un. So on the right hand side, inside the bracket should be all plus. Okay. So what we are doing essentially here is, so let's take, we have the equation. So minus 5x, I'm going to write it as 5x n plus 1 plus 5x n minus 1 by 2. Now this is applied at n. Similarly, dou v by dou t. So all these terms that are responsible for the gravity waves, I am the phi x, dou phi by dou x, I am writing it as a phi x at n plus 1 plus phi x at n minus 1 by 2. So clearly on the right hand side and the left hand side you have n plus 1 in x appearing. So clearly it's an implicit representation. So the solution is not explicitly written in terms of the known quantities at the previous times. Then what I do is, now this delta is nothing but my horizontal divergence. So what I do is I take the derivative of dou by dou x of this term. This I will write in terms of finite difference form. You will see that in next. So I will take dou by dou x of this, then dou by dou y of this, and then add. Okay. So what I will have is I will deal with dou u by dou x plus dou v by dou y at n plus 1. So this term I will get, because if I expand this I will have u n plus 1 minus u n minus 1 by 2 delta t. If I use leapfrog, central difference, similarly here. So if I differentiate I will get dou u by dou x n plus 1. I will have n minus 1 also. This is, so if I add with this I get this term, and this is a term which is here. So I differentiate the u equation with respect to x, v equation with respect to y, add, get this term dou u by dou x plus dou v by dou y at n plus 1, substitute that here. Now this term will be known in terms of n and n minus 1. Okay. Now I substitute it here. So I am going to have, okay, let's look at this. So the divergence delta n plus 1 is ux is basically the derivative n plus 1 plus vy there. So this is nothing but I get this equation by substituting in the continuity equation. I get this equation. Now this equation is what is known as, this is the Laplacian, phi xs plus phi yy at n plus 1 is delta n plus 1. Delta is, so this is n plus 1, this is n plus 1, so again it's an implicit relationship. The implicit nature of the solution hasn't changed. However, this equation is known as a Helmholtz equation. There are very efficient relaxation methods that are available to solve it. So if I solve this equation, Helmholtz equation, I'll get phi of n plus 1. So once I get phi of n plus 1, I can find out phi x of n plus 1. And then I get u of n plus 1. Once I get phi, I can get phi y of n plus 1 using finite difference, I get v. So I get phi, I get u, I get v. And then I can march again forward by applying this same strategy. So this was proposed by Robert in the year 1980, and this is a very, very popular method of solving atmospheric science governing equations. Okay. So next one is, okay, so the spectral method is very, very common, very widely used. All operation centers are moved to the spectral method. So the spectral method is an example of what's called a Galerkin method. Okay. Now, up to now we have dealt with finite difference method. Now the problem with finite difference method, it's lots of problems. Okay. So one problem I will tell which the spectral method is successfully able to overcome. So in the Galerkin or the spectral method, what we do is, so let's take, I have an ordinary differential equation. X lying between A to B, L of u, this is an ordinary differential, let's take linear operator, and this is some function of x, known function of x. I have to solve this. So what we do in the Galerkin method is, my u of x, which is unknown, is written as in terms of what are known as basis functions. So aj are coefficients and phi j's are known as basis functions. So the basis functions are supposed to have nice properties in terms that they should have to be continuous, they have to be differentiable, And so the whole idea is, if I can find out this aj coefficients, j running from 1 to n, I can substitute in the series and get the solution. Okay, so this is also called the series expansion method, or it's also known in literature as Galerkin method. So the spectral method is an example of the Galerkin method. So what you do is, this is of course an approximation. So if you want more accuracy, I have to keep more terms in my expansion, right? So then I substitute this in my differential equation. Differential equation is this LU equal to Fx. So I substitute U with this series expansion. Obviously this is not perfect, so this is not going to be equal to the right hand side. So the difference between left hand side and right hand side after the substitution of U from the series is going to give me an error, which is the error. Now the Galerkin method says the errors have to be orthogonal to the basis function. So the error has to be orthogonal, so that condition is phi j error integrated over dx should be equal to 0. Okay, and spectral methods are basically also having this property that the basis function have to be an orthogonal set. Okay, so this is my error. So then the error, I put the condition of orthogonality, error into the basis function integrated over a to b dx equal to 0, I running from 1 to n. So we have a system of n algebraic equations here. N algebraic equations, so the error now involves my uj, right? Okay, I have written aj here. Okay, so the errors involve uj. So I have a system of so this is the expression. I have system of n algebraic equations involving the uj. Okay. So if I solve this, in principle I have n unknowns, u1, u2 up to un. I have n equations, so I can solve this. So once I solve this, I get this unknown coefficients uj. Once I get this unknown coefficients uj, I can plug it into my series expansion and get the solution. Okay, so an ordinary differential equation reduces to a system of, and the original equation is linear, to a system of linear algebraic equation which can be solved. Now what is the advantage of this method? The advantage of this method is, if this linear differentiable operator, suppose this has derivative with respect to x, dou u by dou x or dou 2u by dou x squared. Once I define this series expansion, the derivative is exact. Suppose phi x is your sin x, right? Dou u by dou x is going to be exact. Dou 2u by dou x squared is going to be exact. So the derivative of the basis function with respect to x, whatever the derivative is going to be exact. Now this is very different from finite difference. In finite difference, any derivative, you introduce error, truncation error. Okay. So here the greatest advantage of this Galerkin method is, once you assume an expansion of this form, the derivatives are going to be exact. So that means you are going to have a much more accurate solution in your Galerkin method solution rather than as compared to the finite difference. So this is the biggest advantage of the Galerkin method, which is why it's widely used. So one can, because atmospheric science equations deals with PDE, so we can deal with PDE also. Okay, suppose this is the same differentiable operator. Now u is a function of x and t, so you have two independent variables, so it's a PDE, right? So it has a time dependency. So again it's the same thing, only thing is your u xt uj now will be a function of time and the basis functions will be functions of x. Okay, that's the only difference. So you substitute this in your original PDE. This is an approximation. So this left hand side is not going to be equal to the right hand side. Left hand side minus right hand side after substituting the approximation gives you the error or the residual. That residual has to be orthogonal with respect to the basis function phi. So when we had an ODE, we got a system of algebraic equations involving the coefficients. When you have a PDE, you will get a system of ordinary differential equations. So the PDE with two independent variables becomes a system of n ODEs. Now each of the ODE, the unknown is dou uj by dou t. duj by dt, because uj depends only on time. Now what we do is, to solve this system of ordinary differential equation, we replace this derivative by finite difference with respect to time. And then knowing what is the solution at the initial time, and knowing what is the uj at the initial time, I can always find out what's the uj from the later time by solving this. So this way you can update. So again the space derivatives are exact. So all the advantages of, so all the disadvantages of finite difference schemes go away. So that's why the spectral model is used everywhere, because of its high accuracy. Okay, now what happens is, in the atmosphere, we all know about the so-called geostrophic balance, right? So in a sense, it's a balance between the horizontal pressure gradient force and the Coriolis force. And the Coriolis force can represent the wind field, the pressure gradient force represents the mass field. So in the atmosphere, you have an overall balance between the mass field and the wind field, which is manifested in the geostrophic balance. Now, whenever there is an imbalance or a departure from the geostrophic balance relationship, then you have the manifestation of gravity waves which will propagate out from the region of imbalance. And when they propagate out, they will restore the geostrophic balance. So this situation, from a state of initial geostrophic imbalance to a final state of geostrophic balance, is called the geostrophic adjustment. Now, whenever we deal with all the equations, typically we deal shallow water or the original 7 equations. These are all hyperbolic, so the solutions all can be represented in terms of waves. And so what happens is, how well the solution is representing your geostrophic adjustment. Or in other words, the question is, suppose I write down the one-dimensional gravity shallow water equation without rotation, linear, okay. This is one-dimensional linear shallow water equation without rotation. Now u and phi are the unknowns. Phi bar is a mean geopotential. Now obviously phi bar is, now we know that is actually related to the gravity wave. So the dynamics of this equation is determined by the gravity wave, external gravity wave, who's got a phase speed of root of gh. Now if you just apply your finite difference scheme as it is in an unstaggered way, that means, so this is one-dimensional with respect to x, these are my grid size. So I represent u and phi here, I represent u and phi here, I represent u and phi here, and so on. I get the numerical solution. This numerical solution has lots of problems. The analytical solution gives you a non-dispersive wave because the phase speed is root of gh. For a constant capital H, the phase speed is constant, right? So obviously only if the case where the phase speed is a function of your wave number, so basically you have a dispersive wave. So the original analytical solution is a non-dispersive wave, but if you do by finite difference discretize space with finite difference scheme, discretize time, and then integrate in time, you'll find that the nature of the solution gives you a dispersive wave. So this is called computational dispersion. The moment you apply the finite difference scheme, you have a solution that is providing waves which are dispersive when the original analytical wave is non-dispersive. Now, there are also other serious issues. One serious issue is the smallest wave has zero frequency and has zero phase speed when you apply for the non-staggered grid. The moment instead of this, you apply it as a staggered grid. So what I do is, in my grid point I prescribe phi, and in my midpoint I prescribe the other dependent variable, and then write down the finite difference scheme. This is called a staggered arrangement of the dependent variables, and this produces better geostrophic adjustment than this. The simulation of the gravity wave is much better in this than in this. Okay, so all numerical weather prediction models all use staggered grid. The most well known of this is what's called the Arakawa staggered grid, which is represented in the left top panel. Okay, similar to horizontal. So here what happens is, so I have this term dou phi by dou x. Now in the staggered arrangement, I have to bring all the term to the u location for the u equation. So dou phi by dou x, I have to bring to the u location. So I have phi here minus phi here by delta x is actually gives me a central difference over delta x by 2. In the non-staggered grid, I have the central difference for the same term over 2 delta x. Okay, so that's another big advantage of the staggered grid. Similar to the horizontal staggered, you can, so if you prescribe all the variables UV, temperature, geopotential and all at, so you discretize the atmosphere also into different layers and you prescribe all of them at these layers. Okay, so this is the center of the layer. Okay, you prescribe everything at all the levels. Sigma dot is your vertical velocity in the sigma coordinates, u, v, t, geopotential everywhere at the end of these layers. Then obviously it's called an unstaggered vertical distribution of dependent variables. Now there are two different ways in which to vertically stagger dependent variables. One is called the Lorentz grid. In the Lorentz grid, each layer you have a mid level of each layer where the vertical velocity, where at the end of the layer sigma dot is prescribed. At the midpoint you have u, v, t and phi are prescribed. This is called the Lorentz grid. There's another grid called the Charney-Phillips grid or the CP grid, in which the sigma dot and geopotential are prescribed at the model layers. At the midpoint of the model layers you have u, v and temperature. Now this is the preferred grid. You can all realize why, because if you know the hydrostatic equation is going to be dou phi by dou p is equal to minus alpha. The hydrostatic equation in pressure coordinates, this is equal to minus RT by P. So in this situation what happens is dou phi by dou P, that means phi here minus phi here by this delta P will be equal to the value of temperature at the midpoint. Now if you apply that here, now phi is here, dou phi here minus phi here by this delta P is equal to temperature. There is no temperature at the mid level. I have temperature here, I have temperature here. So to get the temperature mid level, I have to average this temperature and average this temperature. So averaging is going to smooth out the solution and maybe leads to some loss of information. So we need to avoid averaging as much as possible. So Charney-Phillips grid is the most preferred grid. Okay. So upper and lower boundary condition, I'll skip all these things. There's no time. Huh? So essentially we treat the upper boundary condition in such a way that whatever gravity wave has to get out of the domain, we allow it to go. So that is how. And bottom boundary condition is very complicated because we have to deal with the nature of the surface and then land surface and other things we have to bring in. So physical parameterization, I'll just spend. So as I told you, the moment I've discretized a grid, so I have a wave that can be resolvable, right? So if I have a grid size of 10 kilometers, the wave that is smallest wave that can be resolvable is 20 kilometers. Now we have several processes in the atmosphere that are subgrid scale, right? Now, so you can't ignore this effects of subgrid scale. Suppose if you you take a global domain, yesterday you heard that NCMR WF has a global domain of 20 kilometers. So that means the resolvable is 40 kilometers. So you have so many processes, so many things happen within 40 kilometers, right? So, and these cannot be represented because they are not resolvable. At the same time, you can't ignore their effects. Like for example, you can have several thunderstorms within that 40 kilometer by 40 kilometer square, right? And you say, I forget about all non-resolvable scales and I deal only with resolvable scales, then obviously a lot of useful information So the idea here is the solvable scales you need to resolve. You need to get the solution that describes the resolvable scales. But at the same time, you cannot ignore the non-resolvable scales. What you have to do is you have to find out what is the effect of the non-resolvable scales on the resolvable scales. If you can capture the statistical effects of the non-resolvable scales on the resolvable scales, then you are done. How to do it is what's called the parameterization schemes. So because as you can see, the atmosphere has a wide spectrum of temporal and spatial scales ranging from 1 second to 10 to 6 seconds, which is a day, 86,400 seconds. Spatial range 1 centimeter to a turbulent eddy to 10,000 kilometers. So it's a wide spectrum. Now once I fix my grid size, I fix my resolvable scales. Once, so I'm going to have so many physical processes that are subgrid scale, which I need to parameterize. Now how do you parameterize them? So this is one example of momentum equation. So what I do is in your usual Reynolds thing, what we do is we do it in time. Now here I can take a resolvable wave, and my u bar is nothing but the u of the resolvable scale plus a departure which is represented as u slash. Similarly temperature, similarly pressure. So what I can do is I will write u as u bar plus u prime. So you can see here. So this is a nonlinear term. Obviously, only in a nonlinear term these effects become prominent, because the nonlinear interaction will actually give rise to the contribution of the non-resolvable scales to the resolvable scale, as you can see here. So this term u dou u by dou x, u I write it as this, dou by dou x of this, and then I expand it, I have 4 terms. Then if I want to take the resolvable part of u dou u by dou x, then I have to do the resolvable of all the 4 terms. Then obviously this term remains and this term remains, other 2 terms vanish. So basically what happens is the resolvable scale of this term gives rise to 2 new terms. You can see here, this one and this one. This one is, so now if I write this term, so this is my original equation, and the resolved equation is this. So this term comes and there is one more term here. Okay, so we had this, this is basically a viscous force per unit mass due to momentum transport based on your kinetic theory, and so this is the so-called laminar contribution. So then this can be represented in terms of this quantity. This is your turbulent contribution. So you have to deal with additional stress terms in the momentum equation. So this is what is called your Reynolds stress term, capital T, and this is your laminar, the molecular stress term. So now what happens in each of the equations, u equation I am going to have 3 additional terms, v equation I am going to have 3 additional terms, w equation I am going to have 3 additional terms, temperature equation I am going to have 3 additional terms. So my total number of unknowns has now become much larger than the total number of equations that is available to me. Okay, so how do you resolve this issue? So one thing is I attempt to find out what is the evolution in time of these new additional terms that appear, the so-called Reynolds stress. So I can derive the equation for that. If I derive the equation, I end up with terms that are third moment equations. So I'll have u prime, w prime terms coming. So if you write down the evolution of the third moment equation, you get the fourth one. So there's no closure. So that means this is a fundamental problem of turbulent flow. In this case, we are not looking at it in terms of time. We are looking at it in terms of space, the averaging or the resolvable length in terms of space. And so this is a closure problem, classical closure problem. So we get around a workaround solution for this by forcibly closing it. And that's what is done. So these new Reynolds stress terms are written in terms of the already known unknowns. Now we have various first order closure schemes called the K theory, and so I think this is something which, so this is in a sense the small unresolved scales which are represented by the Reynolds stress terms, they can be represented in terms of the resolvable scales. So that is one way of physical parameterization. Okay, this will be my last need for data assimilation. So first we have to, suppose I have a global model. Let's say half a degree is my grid size. So obviously 0 to 360, I have 720 grid points in my east-west. In my north-south, from 90 north to 90 south, I have 180. So this is the number of grid cells I have. And if I discretize the atmosphere into 50 layers, this is the total number of volume cells I have to discretize the entire atmosphere. Half a degree in lat long, 50 layers discretized in the vertical. And I have 7 dependent variables. So this gives me the total number of degrees of freedom. This is something like 10 power 7. Okay. Now, in order to prescribe the initial state of the atmosphere, I have to give this 10 power, like 720 into 180 into, sorry, this is 360. This is half a degree, right? So I have to prescribe this 10 power 7 numbers. 10 power 7 numbers of U, 10 power 7 numbers of V, 10 power 7 numbers of W, 10 power 7 numbers of temperature, geopotential, what. So, and we know 70% is over the sea. We don't have any observations. So how do we prescribe the initial state of the atmosphere? The requirement as proposed by Biagni said 2 requirements. One is I have to prescribe the initial state of the atmosphere. I should know the equations that govern the evolution of the atmosphere as a system. I have now encountered a problem. I don't have the observations. Okay. So of course here it's a coarser resolution 1 degree, 50 layers. So you have 3.24 into 10 to the power of grid points. If you multiply it with 7 variables, you have this 2.2 into 10 to the power of 7 values. So that's 10 power 7 is your degrees of number of freedom. But the maximum observations that you can get, including all possible, is 10 power 5, 10 power 6. So there is still an order or 2 orders less observations. Now how do we resolve this? So we can't prescribe the initial state of the atmosphere. That means I don't have enough observations, so maybe I have to interpolate. Interpolation gives rise to errors. An atmosphere is a chaotic system. The initial errors are going to grow. After some time, I'm going to lose my ability to forecast. So there's lots of issues. So how do we get a workaround solution for this? Okay. It became clear that in order to find this out, we have to have what's called a background. I think what's also known as a prior. All of you have had various lectures that you have heard to last week and also yesterday. So basically, we need to have the complete first guess estimate of the state of the atmosphere. That's what's called the background. So initially, people thought I can use the climatology as a background. But then once the models started becoming more and more accurate, it was thought the best thing to use would be the model output itself as my first guess of the background. So that is what is now applied for the data assimilation. So basically what data assimilation is, it sort of integrates all possible observations and then combines it in a very optimum way with the background of the first guess, which is the model output, to get you the best estimate to set up the initial condition of the atmosphere that you can run for a numerical forecast. I think I've just completed. So I'm sorry I had to go a little fast towards the end. And okay, thanks.